answer all the hard questions. Okay, so let me start with the paper. So what's the main idea of the paper? The main idea of the paper is to give you what the title says, testable restrictions on asset pricing models. So basically what we give you here is a machine that allows you to test any type of asset pricing model that you may have in mind. I cannot now. Okay, so as you know, any type of asset pricing model is typically summarized by the stochastic discount factor. Let me remind you of your first asset pricing PhD class where you learned about the Hansen-Jagannathan Unbound. So the Hansen-Jagannathan Unbound tells you the necessary condition for the admissible set of stochastic discount factor given a vector of asset returns. And here is the formula. So on the left-hand side, you have the standard deviation of the stochastic discount factor, which is unknown. Okay, so on the left-hand side, what you would do is you take any type of like asset pricing model that you have in mind. And on the right-hand side, you have something which is observable, which in the case of the HJ bound is going to be the maximum Sharpe ratio in the economy. So what we have learned in the past 30 years is that the volatility of the stochastic discount factor should be at least the maximum Sharpe ratio in the economy. So two reasons why the HJ bound has become so useful is because it provides a test of an asset pricing model based on observable returns. And second, it also provides information on how we should modify the stochastic discount factor in order to be consistent with the data. So let me just give you one quick example. So in this case here, we're plotting the HJ bound, and on the x-axis, we have the mean of the stochastic discount factor, which is around 1 because the gross return on the risk-free rate is around 1. And on the y-axis, we have the standard deviation of the stochastic discount factor using S&P 500 data. So what you see here is like the equity premium puzzle that like has allowed us to do asset pricing in the past 30 years. And why is that? Because if you take like just a standard consumption-based stochastic discount factor, we know that the stochastic discount factor, the volatility, should be risk aversion times the volatility of consumption, because volatility of consumption in the US is around 2-3%. You need a risk aversion of at least 30 in order to match the 60% that we see in the data. Okay, so what have asset pricers been doing in the past 30 years? Well, they put in other state variables into the stochastic discount factor, like long run risk or habit. Okay, so this is how we learned what to do once we failed the HJ bound. Okay, so what are we doing in our paper? So while the HJ bound obviously are very powerful, they're only necessary but not sufficient. What does that mean? It means that we don't use all the information that we have in asset returns in order to test asset pricing models. And I will be very clear what I mean with all the information in asset returns. What we do in this paper is that we develop a novel systematic approach to test asset pricing models with a particular focus on obtaining testable restriction on the joint distribution of multiple stochastic discount factor. Okay, so in the HJ bound, what we do is that we test one stochastic discount factor using one set of returns or just the first two moments of the return distribution. However, there are many applications, and I will give you many examples where this particular setting is not useful and cannot be used. Okay, and I will give you the examples in a minute. So what we do in the paper is that we take a set of empirical and theoretical restrictions. So by a theoretical restriction, for example, you can think of an Euler equation as primitives. And what we're going to do is that we're going to return a family of necessary conditions that the joint distribution of stochastic discount factors have to satisfy. Okay, so let me give two examples where we want to use like a multivariate stochastic discount factor. The first application we had in mind is in international finance. So I work, for example, in international finance. And in international finance, we usually care about two stochastic discount factors because it's all about two different countries. So for example, what we want to do or what we're interested in is the joint distribution between one stochastic discount factor, take the US, and the second stochastic discount factor, take, for example, the UK. So what we want to do is we want to have restrictions on the joint movements between two stochastic discount factors. HJ does not allow us to do that. A second application we have in the paper is the joint distribution between permanent and transitory component. So as you probably know from the famous Alvarez-Yerman paper, we can always decompose a stochastic discount factor into two components, a permanent and a transitory component. And what we do in this paper is that we also provide restrictions on the joint distribution between permanent and transitory component. If you tell me I have never cared in the past 20 years about permanent and transitory component, and I will never care about that, that's fine. I will show you that there are economic applications where this is actually an important quantity that we should care about. Okay, so let me start with the framework. So here's just some notation in order to introduce the framework. So let me start with two definitions. So R is going to be a vector of returns. This vector of returns is very general, so this can be anything. Okay, so this can be equities, this can be bonds, this can be options, whatever you want. Returns of different countries. It can really be any type of return. M is just going to be a vector of positive random variables, which of course in our application are going to be stochastic discount factors. So think of M1 to MK as stochastic discount factors of different countries, or pricing kernels that price returns over different horizons. For example, there's a large literature that now studies downward sloping term structures of risk. So if you want to do that, you want to look at term structures with different horizons. Or, as I mentioned before, we can look at the distinct frequency components of pricing kernels, a la Alvarez and Yerman. Okay, so what's the main goal? The main goal of the paper is to obtain testable restrictions on the joint moments of M in terms of observable moments. So what do I mean by observable moments? We have two ways of thinking of observable moments. The first one is an obvious one. It's similar to what we just saw in the HJ bound. It's what we call an empirical observable moment. In this case here, we think of the statistical properties of asset returns. Okay, so think of the mean, the variance, the skewness, and the kurtosis and whatnot of the return distribution. The second set of observable moments are what we call theoretical moments. And these could be, for example, any type of constraints that are imposed by your asset pricing model. 99.9% of all asset pricing models, for example, impose a no arbitrage restriction. So a no arbitrage restriction is what we call a theoretical observable moment. So what's the idea? The idea of the paper is very simple. Let's take these observable moments and let's try to bound the unobservable moment of the joint distribution of stochastic discount factors. Okay, so here's the main object that we're interested in this paper. So the main object is going to be this cumulant generating function, which is just the expectation of the stochastic discount factor M to any power M and the return vector R to a power R. Okay, so this O is going to be the set of observables, which is just going to be defined as this object here, which is going to be the object that we want to bound with the observables that we impose. Let me give you an example that's already known in the literature. Okay, so in the univariate case, we can go back to what Hansen and Jagannathan have been doing. So in the univariate case, we have a single return R, and we have a single stochastic discount factor M. So what are the observables that we have? So we have the return distribution of R, and we have a pricing restriction, which is the no arbitrage restriction or Euler equation, which tells us that E of MR has to equal 1. So how does the set of observable look like in this case? In this case, we have 0 R, and why is that? Because the return distribution of R is E of M times R. So M is to the power 0 and R is to the power R, because we assume that we observe all the moments of R. And we have the point 1, 1, because the Euler equation is E of M to the power 1, R to the power 1 equals 1. So we have these two restrictions on the set of observables. So how does that look like? So here's just a graphical illustration of what we have in mind. So on the x-axis, we have all the powers of the stochastic discount factor m, and on the y-axis, we have all the powers of the return vector r. Okay, so this line, this red line here is the return distribution, because here we are in the power of the stochastic discount factor is 0. So these are all the moments of the return distribution. So this would be the mean, this would be the variance, and so on. This dot here is the Euler equation because it's m to the power 1 and r to the power 1. So this is just the dot here. So what we want to do in this paper is we take these observables, which are the red line and the red dots, and we want to bound the unobservable moments using these observables. Okay, so what we want to do in this paper is derive upper and lower bounds using the set of observables. Okay, so this was nothing new, the univariate case. This example here is the international example, which is more interesting because it really extends the literature. So in the international finance application, we have a setting where we have two countries, and we have, for example, the US and we have the UK, and we have two return vectors, R1 and R2. Importantly, we don't impose any restrictions on the market structure. What does that mean? If you have segmented markets, for example, meaning that US investors cannot trade UK assets, the return vector 1 are just going to be the US assets. Take short-term bond in the US, equity in the US. If you have integrated market where US investors can also trade UK assets, you just add the UK assets to the return vector 1, which is the returns which are traded by the US investor. Okay, so whatever your market structure is, you're just going to adjust your return vector based on like whether you have segmented, partially segmented, or integrated markets. So how does the set of observables look like? So we have the joint distribution of returns, R1 and R2. In any international finance application that I can think of, we usually assume that the Euler equations hold. So we have a domestic pricing restriction. So that would be the Euler equation in the US. And then we have a foreign pricing restriction. Think of the Euler equation in the UK. So how does the set of observables look like? Now we have 0, 0, R1, R2. Why is that? Because all the powers of M are 0, and we have powers R1 and R2. Then we have 1, 0, 1, 0, because we have an Euler equation in the US. So all the powers of the UK are equal to 0. And by the same token, we have 0, 1, 0, 1, which is we make all the powers in the US 0 and all the powers in the UK equal to 1. Okay, so last example. So if we have a dynamic asset pricing framework where we want to decompose the stochastic discount factor into a permanent and a transitory component, we have the following restrictions. So Alvarez and Yerman argue that you have this martingale restriction on the permanent component. And the second restriction we have is that the transitory component of the stochastic discount factor is just the inverse on the gross return on the infinite maturity bond. So what does this imply? It implies the following observable sets. So now we have 0, M2, and R. So what is that? So this is the joint distribution of returns together with the long-term bond. And why is that? Because the long-term bond obviously has to be in the set of observables in order to impose this restriction here. Then we have 1, 1, 1. That's because the permanent component is to the power 1, the transitory component is to the power 1, and then we have the return vector. And then we also have the martingale restriction, which gives you a power, sorry, so here we mixed up P and T. So we have a power 0 on the permanent component, a power 1 on the transitory component, and a power 0 on the return component. Okay, so this was just notation. Apologies if this is very notation intense. Let me get to the main result. So here's the main result. So the first result we have is that we derive an upper, what we call upper Jensen bound on the set of observables. So here, what we have here is just the convex hull on the set of observables. And our first result tells us that we can always upper bound the cumulant generating function of M and R using this expression here. Okay, so what is this J upper bar? This J upper bar is just the solution of this optimization problem where we optimize over the convex combination of all the points in the set of observables. So where does this, so if this looks very complicated, just think of it similarly to what we just saw in the Hansen-Jagannathan Unbound. On the left-hand side, you have something which is unobservable, which are the moments of the joint distribution of the stochastic discount factors. And on the right-hand side, we have something that we can calculate from the data. So where does this result come from? This result is just a consequence of the fact that the cumulant generating function is convex in its argument M and R. And at the same time, we also take advantage of the fact that we can apply Jensen's inequality, and that's why our paper is called Jensen bounds, that allows us to upper and lower bound this object here. Okay, so what's the idea? So when M and R are in the convex hull of the observable set, it can always be expressed as a convex combination of points M tilde and R tilde, which are also in the observable set. Now, Jensen's inequality tells us that we can always upper bound the CGF by the convex combinations of points M tilde and R tilde in O with the same weights. Now, because we take the infimum over all these convex combinations, we make sure that we get the tightest possible bounds. Okay, so this sounds now very abstract. I will show you later on in the applications that I just showed you that we can get expressions which look like more accessible and that we can actually use in the data. Okay, so here's just an illustration of what I had in mind. So remember, in the univariate case, we assumed that you observe the return distribution R, and we also impose that the Euler equation has to hold, which is the red dot. So these are all our observables, and the gray shaded area is just exactly the convex hull that I was discussing before. So what's the idea? The idea is that any convex combination between the red line and the red dot are going to lie within this convex hull here. Okay, so this was for the upper bound. We can also derive a lower bound, as in the case of the Hansen-Jagannathan Unbound. So in this case here, we are going to define an O lower bar, which implies that there exist convex combinations of points X and O that fall within O. And in this case here, we can derive a lower bound on the cumulant generating function, where again, this lower bound J lower bar is going to solve this optimization problem here. Again, so this is just a repetition. This is just a consequence of Jensen's inequality. So basically, the idea is exactly the same as before. We can derive a lower bound based on the observables we have. So how does it look like in our graphical illustration? So here we have the set of observables, which are the red line and the red dots. And in the case of the upper bound, we're now just going to be outside of the convex hull. Here are just two consequences of the results that we have, and then I will get to the application. So the first consequence is obviously if M and R are within the set of observables, the bounds are going to be tight. This is obviously a direct consequence of the results we have. This result here tells us that if you enlarge the set of observables, so if you add more and more observables to what you have, for example, if you add option returns to the set of returns, the bounds are obviously going to get tighter and tighter. This is very intuitive. So obviously, the more restrictions you have, the more you can pin down the moments of the joint distribution of stochastic discount factors. Okay, so this was very abstract. So now let me get to the characterization results, which allow us to do the applications. So here's just the first result we have, which again is nothing new. So this is just a sanity check that we can recover the results that we have in the literature, which are in the univariate case. So remember, in the univariate case, we have a single stochastic discount factor, and we have a pricing vector of returns. In this case here, we can calculate in closed form what the upper and the lower bound are going to be. So what does this result tell us? It tells us that we can upper and lower bound the moments of the stochastic discount factor. So if alpha takes different values, so if alpha is equal to 1, we have the mean. If it's equal to 2, we have the variance. We can always bound it by the return distribution here. So obviously, if alpha is equal to 2, this result here just reduces to the Hansen-Jagannathan bound. Okay, so the variance of the stochastic discount factor is just going to be bounded by the maximum Sharpe ratio that we have in the economy. If alpha is equal to 0, we can recover the entropy bounds of Alvarez and Yerman. So the entropy of the stochastic discount factor is going to be bounded by the entropy of the return distribution. More generally, we can recover the family of bounds in Snow. So Snow has a paper in the JF where he derives the bounds on all the moments of the stochastic discount factors. Okay, so this result here is nothing new. So this is just a sanity check that our framework gives us the results that we have in the literature. Here's the new thing that we have in the paper. So remember, we had this international finance case where we had 2 stochastic discount factors and 2 sets of returns. And we also imposed that the Euler equation in the domestic and in the foreign country has to hold. In this case here, we can again derive an upper and a lower bound on the joint distribution of 2 stochastic discount factors. So in this case here on the right-hand side, you can derive in closed form any restriction on the joint distribution between M1 and M2. Now, of course, if, for example, alpha is equal to 2 and beta is equal to 0, you recover the HJ bounds, which are just going to be on the marginals of the 2 stochastic discount factors. I will show you in the application what we mean. Okay, so maybe you tell me, well, what is this object on the left-hand side? This is just some very weird object. You take M1 to the power of alpha, you take M2 to the power of beta. Why do I care about the 50th moment of M1 and M2? Well, so the reason why we're interested in that is, for example, many people in international finance usually assume that the 2 log stochastic discount factors are jointly normal distributed. So if you look, for example, at the reduced form models that Lustig and others have, they usually assume that M1 and M2 are jointly normal. In this case here, we can calculate expressions which probably look more familiar to the average user of international finance. So in this case here, for example, we can bound the covariance between the log stochastic discount factor between 2 countries. Now, why do we care about this object? Well, in international finance, we care a lot about the joint co-movement between M1 and M2 because it's informative about the risk sharing between 2 countries. Okay, so the higher this correlation is, people say the more risk sharing there is between 2 countries, the lower this correlation is, the less risk sharing between 2 countries there is. Now, the problem in the international finance literature is that we need to assume a very high correlation of these 2 stochastic discount factors in order to match the puzzles that we have in international finance. But what people argue is that this correlation is not very high in the data. So it's very hard to find 2 macroeconomic variables which are very highly correlated. Now, our application allows us to give us bounds on what these correlations or covariances are supposed to be. So here is just an illustration of how this looks like in this international case. So the blue triangle is going to be the upper bound. So on the x-axis, you have all the powers of the domestic foreign stochastic discount factor. On the y-axis, you have all the powers of the foreign stochastic discount factors. The red dots here are just going to be the HJ bounds. Why is that? Well, if you take alpha to the power of 2, you get to the variance of the US stochastic discount factors when beta is equal to 0, and vice versa. You have the same for the foreign stochastic discount factor. Okay, so keep this picture in mind because we're going to use this picture in our application. Okay, so last theoretical result, and then I will get to the application or the data, which hopefully is going to be more interesting. So in this case here, remember, we wanted to look at different frequency components between permanent and transitory components. So in this case here, we can also calculate in closed form what these bounds are. So these are now just going to depend on the joint distribution between the infinite maturity bond and the return vector R. Okay, so this is something that we can calculate, obviously, using the data that we have. Again, we can calculate the corollary. So if we assume that we have two log stochastic discount factors, we can again bound the covariance between the transitory and the permanent component. I will show you, if I have time, I will show you why the covariance between the transitory and permanent component is an interesting object that you should care about. Okay, so let me get to the applications. So in the first application, what we want to do is we want to take a very standard international finance model, and we want to see, do we see any, are the bounds that we have are informative about where we see, for example, rejections of this particular model. So I have nothing against Max and Rick, they're good friends. The reason why we took this particular model is just because this model fits all the asset pricing puzzles we have in the data. So we have international finance asset pricing puzzles, and we have the equity premium and the risk-free rate puzzle, and they match all these puzzles. So what we want to do is we want to take their stochastic discount factors and see whether their SDFs fit our bounds. So in this application here, we have two countries. We have the US and we have the UK, and each country produces a good X and a Y. The consumption in these two countries are just going to be as follows. So this is very standard. So this is the consumption of good X produced in the US, and this is the consumption in the US of the good produced in the UK, and they're raised to the power kappa, where kappa measures the degree of home bias. So in international finance, people usually assume, and what you see in the data is that people prefer the goods that is produced in their own country. So if kappa is larger than 1/2, you prefer your local good more than you prefer the foreign good. And the symmetric happens with the consumption in the UK. Obviously, because we want to match asset pricing puzzles, we're going to assume a utility function which deviates from the standard power utility. So in their case, we have Epstein-Zinn preferences. These are just standard Epstein-Zinn preferences where we assume that people have a preference for early resolution of uncertainty. The goods market has long run risk. So the good that's produced in the US has this permanent component, the persistent component Z, and the good that's produced in the UK also has a persistent component Z, where rho J is just going to be 0.99 or 0.98. The shocks that affect the persistent component is what people in the long run risk literature call long run shocks. Why? Because they have an effect on your continuation utility, and the shocks epsilon X and epsilon Y here are what we call the short run shocks. Okay, so there's nothing new here. What we do now is we take the stochastic discount factor in each country. So we have a stochastic discount factor in the US and we have one in the UK. We simulate their stochastic discount factor using the parameters that they give in the paper. And then we try to derive the bounds using the return data that we have that are assumed in the paper. So in the paper, Max and Rick assume that agents can trade the risk-free bond in the US and the UK, and they can trade the equity in the US and the UK. Okay, so it's a fully integrated market where everyone can trade all the assets that are available. So what we do is we just download the time series of returns and we optimize the bounds that I have just showed you using this return data. What we then do is that we compare the bounds that we calculated from the return data with the moments that we can calculate using the simulated stochastic discount factor in the US and the UK for all powers alpha and beta. And what we then do is that we obtain bootstrap p-values for each of these estimates, alpha and beta. Okay, so what we do is we just compare how many times did the model violate what we see in the data. And this is So before I get there, these are the parameters that people use in the literature. So risk aversion is 6.5. IES is equal to 1.6. Discount rate is 98%. Home bias is extremely high. It's 97%. The average growth rate of consumption is 2%, and the average volatility is 2%. As I said, this is a very successful model. Why? Because it matches the equity premium, it matches the risk-free rate puzzle, it matches all the exchange rate moments that we have, it matches violation of UIP, and it matches the Becker-Smith puzzle. So what do we get if we calculate these bootstrap p-values? So remember, we have both upper and lower bounds for the moments of the joint distribution between the US and the UK stochastic discount factors. And each of these colors are just going to indicate a different p-value. Okay, so yellow will be a p-value between 50% and 100%. And the darker shaded areas just indicate that you have lower p-values, meaning that these are the areas where we reject the model. So to remind you, on the x-axis, we have the powers of the US stochastic discount factors. On the y-axis, we have the powers of the UK stochastic discount factors. So let me first get to these red dots here. So what are they? So these are exactly the HJ bounds. Why is that? Because we take alpha to the power of 2 and beta is set to 0. By the same token, we have beta equal to the power of 2. So that's the UK, that's the variance of the UK stochastic discount factor. So if I go and read what are the p-values in this case, I would find that the p-value are 7.26 and 7.22. What does that mean? It means that if you take conservative levels of statistical significance, you would say, well, it passes the HJ bounds, okay? Now, obviously, here, there's nothing new. So Max and Rick, even in their paper, they mentioned that their stochastic discount factors pass the HJ bounds. Where it gets interesting is where we see violations when we look at the joint distribution of two stochastic discount factors. Okay, so if you, for example, move into the negative quadrant of where we have for the UK stochastic discount factor and the US stochastic discount factor, what you see here is that all the p-values here are between 2% and 5%, meaning this is where we reject the model. Now, why is this an interesting result? Well, this is an interesting result because if you think about the joint distribution of two stochastic discount factor, this is where the skewness of the joint skewness of two stochastic discount factor matters. So how can you see that? So the way we can see that is by calculating the dispersion of the two stochastic discount factors, M1 and M2. So these powers, alpha and beta, so basically what they do is that they inform you how much weight do we put on the moments of the stochastic discount factors. So obviously, alpha puts weight on the moments of the US stochastic discount factor. So for example, on the variance and the skewness of the US stochastic discount factor. Beta gives you the weights on the variance and the skewness of the UK stochastic discount factor. However, because we are interested in the joint movements between the US and the UK, we can also look at co-movement, so co-skewness between the US and the UK. And what we see here is that you see all these violations in the co-skewness between the US and the UK, indicating that the model that we have here is probably not very good at explaining the co-skewness that we have in the data. We know, for example, in the data that when you have like big negative shocks in the economy, take, for example, COVID, that you see asset returns both in the US and the UK falling at the same time. What our bounds are telling you here is that this violation indicates that these moments are probably not very well captured by the model that we have, that Rick and Max have written. But obviously, it would be very easy to address this point. Why is that? Because you can just introduce, for example, joint rare disasters in the aggregate consumption dynamics. Okay, so Neil, timekeeper.
So let me jump in. So you're great on time. You have 15 minutes, but since you took a break, let me ask a question that I've been thinking about for a long time.
Okay.
So all models are wrong.
Yeah.
So if you look at enough higher order moments, you're certain to right? You're certain to reject the model. You're almost certain to reject the model. So, in some sense, it seems like maybe your bounds are too tight, right? So the question is which moments are interesting? Right? The model, no one really takes the model seriously.
Yeah.
I mean, sorry, it takes a model seriously in terms of a qualitative description, but no one really thinks you're going to capture all moments.
Yeah, so first of all, great question. And Piotr, Ali, and Fabio, please jump in. So first of all, we didn't want to write the paper and say, look, we developed this very complicated machinery, and I'm going to show you that your model sucks at matching the 50th moment. That's really not what we wanted to do. So I completely agree with you that any model is going to fail higher order moments. Why? Because this model was never written to match the third moment or the fourth moment of the distribution. It was never meant to. So I think our contribution is twofold. First of all, we are interested in the joint. I think where our application gets interesting is looking at joint moments. Okay, so for example, joint skewness or joint like kurtosis and things like that. Why is that? Because in the international case, as I said, we're interested in joint rare disasters, take COVID or take the war in Russia, which has a negative impact on many countries at the same time. And then another thing is many of these higher order moments we don't really observe, right? I mean, like even if I have all the data in the world possible, many people would argue it's very hard to actually measure the fourth moment. So I don't think it's very informative, for example, to look at the fifth moment, because I mean, it's just not something that we know we can capture.
So that's another question. So your bootstrap.
Hey, sorry, can I jump in 1 second?
Right, of course.
So I think there's one thing to realize, which is the fact that there are some regions where a violation is more serious than others. So there is the issue here, of course, that on the one side you talk about violating some type of moment, but on the other side we don't know first whether some moment exists in the data, and second, higher moments are going to be very difficult to estimate. Now, there are, however, regions here where just by your arbitrage conditions, you know that some moments will have to exist. So, for example, if you force some asset passing condition like expectation MR equal 1 and so on, you know that once these points are fixed, every point in the convex hull of these points will have a moment which exists. So in this graph here, for example, it means that all the regions of the triangle where the axes are between 0 and 1, you know that if you believe in your surpassing constraints, there the CGF has to exist. So in other words, the violation you see there is very likely not due to the fact you are trying to fix some crazy moment in the data, simply because by construction there, those moments have to exist if you believe you are surpassing constraints. So in other words, the violation you see in the triangle are conceptually much stronger and robust than those that you see in other regions, which are not in the convex hull of points where you know the value of CGF is observed by the unsurpassed constraint. Just a remark.
So let me ask another question about the sort of bootstrap exercise to get the p-values. Are you, it seems that there's going to be some moment that's, I'm not sure how to articulate this, right? Do you look, are these p-values looking at each restriction individually? I mean, it seems that, there's going to be some probability that at least one restriction is violated, right? So I think the interesting exercise is not, what's the probability that a particular restriction is violated, but that there's at least one restriction that's violated, which will be, I think, a different probability.
Yeah, so the test here is testing individually for every power, the null that the bound is not violated. So you could correct this for a multiple testing kind of issue, essentially.
Yeah, that's what I'm trying to get
by
at.
jointly simulating, if you want, the value statistic for every power, and then computing the corresponding confidence interval while accounting for the multiple testing problem. Yeah.
All right. Does anyone else have any questions? Actually, since I think Andrea is doing well on time. Please feel free to jump in if you have a question.
Maybe just related to what Fabio said about the triangle. I don't know if I'm just kind of lacking intuition about what's going on here, but these yellow lines that do kind of contours, they're not there to make it cute, right? They're actually kind of p-values that do fit, right? So what do they mean, for instance, in the triangle, the fact that you have kind of some sets of moments that seem to be, is it kind of a statistical fluke, or is there some intuition to gain from these?
So Piotr, you're the expert on the cute lines.
Yeah, so like maybe Andrea should be distributing the questions to the other members of the team. So the orange lines basically are there to delineate your to better delineate the areas where you have different p-values.
Okay.
So they
And you
are
should think
they're cute lines.
They're just cute. Okay,
Just
okay.
cute.
they are, I mean, they are cute, right? But the question Christian is asking is basically about the fact that in different points for different alphas and betas, these tests have kind of different power. And while these test statistics are strongly correlated to what Neil was alluding, that we should just basically correct for that, these tests have different powers because they combine different moments of the stochastic discount factor, right? And you would see that better if you went back to Andrea's expansions, right, where you had skewness, co-skewness, and so on. And basically these come with different coefficients into this triangle, for example, right? And this is where you would see that every single one of these points is a different combination of these. So if you have a strong violation, for example, in the last co-skewness term, it has different importance in different places, right? If it's more important, that it contributes to a stronger violation and a lower p-value.
Thank you.
Okay, Andrea, please go ahead.
Okay, I think, Neil, I'm up with time, right? I mean, I can talk about.
Well, you have, I think you have 7 minutes.
Okay, fine. Okay, so this is new to some of my co-authors, so let me present this. So this is our second application. So in this case here, we always had this question: why should I care about the joint distribution between the permanent and transitory component? I've been doing asset pricing for 15 years. I never cared about it. Why should I care about it now? And here's an attempt on trying to why should we care about that? So Alireza and Yerman, in their working paper version, not in the published version, they show on their fairly general conditions that you can write down the term premium on the infinite maturity bond as follows. So this is just the return on the infinite. So this is term premium. And if they show that the term premium depends on the variance of the transitory component and the covariance between the transitory and the permanent component. So what does this tell us here? It tells us that all asset pricing was always about the permanent component since their paper. Why is that? Because what they show in their paper is that in order to match the equity premium, you need a very volatile permanent component. In fact, all the volatility of the stochastic discount factor is the volatility of the permanent component. Now, here, what I tell you is that the covariance between the transitory and the permanent component is important if you want to explain, for example, term premia at the long end of the term structure. So in particular, the sign of the transitory and the permanent component matters. So what we want to do here is, remember, I gave you an expression for the joint under log normal conditions, what the bounds will be on the covariance between the transitory and permanent component. So what we did here is that we took short-term interest rates, we took a long-term bond, and we took returns on the S&P 500, and we just calculated what these bounds would be. And here, this is here what we get. Okay, so this is very preliminary work. So Piotr did all the work here. So it's not important what the exact numbers are for the time being. What you see here is that we both get positive numbers. So the yellow stuff would all be positive, and we get negative stuff. Okay, so for some powers 2 and 1, what we get here are some positive numbers, and then we also get some positive numbers here and some negative numbers here. So why is this interesting? Okay, so without focusing on what the exact size of what that is, what we thought about is, let's go to some canonical acid pricing models that we have, and let's check what do these models imply, what the sign of the covariance between the transitory and the permanent component should be, and let's compare whether we get anything that resembles what we see here in the data. So if you just take a standard long run risk model, and I don't want to walk you now through all the math, this is just a very standard Bonsall-Yaron long run risk model. If you calculate the conditional covariance between the transitory and the permanent component, what you get is this expression here. Now, what you see in this expression is, as long as people have preference for early resolution of uncertainty, this covariance term here is always going to be negative. Okay, so because all long run risk models assume that agents have a preference for early resolution of uncertainty, what this means is that, well, what we see here in the data is that you do get positive numbers. However, their model by construction is only going to get a negative covariance. Now, what does this imply? It implies that, for example, if I wanted to calculate this term premia here on the very long-term bond, it could have counterfactual implications because the sign of this covariance here is negative. So this is just one example. Now, what about habit? So you can take a standard external habit model of Campbell and Cochrane. You can do exactly the same exercise as before. You can calculate the conditional covariance between the transitory and the permanent component. And what you see here is that this covariance is always positive by construction. Now, why is that? All the shocks that we have in the external habit model are shocks to consumption growth and shocks to the surplus consumption ratio, which determines the habit level of the representative agent. Now, by construction, they are always positively correlated. Why is that? If you have a negative shock in consumption, obviously the habit level or the surplus consumption ratio is also going to drop, and hence your habit level is going to drop. So by construction, you're always going to have this positive correlation between the transitory and the permanent component. Now, again, why does this matter? Well, it matters because in the data, we see both positive and negative covariances. Okay, so this is our paper again. So this is a very preliminary version of our paper. What we do in this paper is very simple. We provide upper and lower bounds on the joint distribution of stochastic discount factors. So the reason why we wrote this paper is because many applications that we have in asset pricing are not just about the marginals, they're about the joint distribution. We have as special cases, obviously, what people have derived previously, and it can be applied to a wide set of asset pricing models. If you have any suggestions or any ideas of what we could do in addition, we're very happy to hear. Thank you very much for attending this talk, even though it was outside of the standard virtual derivative workshop topics.
Andrea, thank you. So now we'd like to invite anyone. Feel free to unmute yourself and ask your question using your microphone. It's your opportunity to tell Andrea she's wrong, or to ask her whatever question you want to ask her.
I think my paper was even easier than the Bitcoin future paper, and that's why no one has a question.
Well, I think no one is going to challenge your mathematics at this point. So,
yes, I think it's fair to say that we all have some digesting to do with the maths and everything. Thank you so much, Andrea. Thank you everyone for having been here. We the next seminar on the other side of the arrival of spring in 2 weeks with Jinton Zan, and then the last seminar with Viktor Todorov. We hope to see you there again. In the meantime, thank you again.